Thank you, Manas. Today, I'm going to talk about confinement to confinement in QCD, SU and gauge theory as a PT phase transition. And my talk will be based on this, particularly this paper in Nuclear Physics B in 2019 with my one of my postdoc, Haresh Rawal. And the initial discussion is based on my earlier works on PT phase transition. So I have listed some of them. Before going to the discussion in the PT symmetric quantum field theory and phase transition, I would like to discuss few examples to highlight typical characteristic of PT phase transition in various system, one-dimensional, higher dimensional, exactly solvable, quasi-exactly solvable, and relativistic quantum mechanics. Okay, so before I go to the discussion on PT phase transition, let me give a very brief introduction. Of course, you had a lot of introduction on PT symmetric system. If you have a theory with antilinear symmetry, suppose H comma A commutator 0 and A is antilinear symmetry operator, then you can have two situations. Either you will have that H and A will have simultaneous eigenfunction, or they may not have simultaneous eigenfunction. If they have simultaneous eigenfunction, so it is unbroken phase. If it not, then they are in the broken phase. So in unbroken phase, you have interesting development that we can have a consistent quantum theory with real spectrum, complete set of orthonormal eigenfunctions, and positive definite norms and unitary time evolution. But you have to go to a modified Hilbert space with a different inner product. And that inner product is CPT inner product, and C is like a charge conjugation. It is not the charge conjugation, but it's similar to charge conjugation. Additional symmetry, which is associated with any PT symmetric non-Hermitian system having these properties. It's a symmetry. It's not independent of PT, and also, sorry, this would be PTC commutator should be 0 independent of C, and C squared equal to. So on the other hand, broken phase, it is not possible to have a consistent quantum theory. So a lot of interesting physics happen at the point when the system goes from unbroken to broken, or broken to unbroken, and that is the PT phase transition point. So this is the elementary introduction of PT phase transition, but I'll focus on the PT phase transition in SU and gauge field theory. Before that, let us consider few examples in quantum mechanics. First example, I consider a spin-half particle in the external magnetic field coupled to harmonic oscillator through this non-Hermitian term. And these are all the usual meaning. And if you consider your magnetic field to in the z direction for simplicity, then you can immediately see that this 0, half. I use the usual conventional notation. This first is the quantum number corresponding to A dagger A, and this is the quantum number corresponding to the sigma z. Okay, and then this is the ground state you can immediately find. But however, if you go to the state with 0 half, this is minus half, 0 half, it is not an eigenstate of this system. But interestingly, this along with 1 minus half state form a invariant subspace of this system. So this actually, the action of this will be in this 1 minus half state, and if you have a 1 minus half state, it will be within this. So it will be an invariant subspace, and we can have general invariant subspace for this system consist of n half and n plus 1 minus half system. So we can have the off-diagonal Hamiltonian matrix for this system, this invariant subspace, and for these two states, it is like this. And now, if we have to the eigenvalues or eigenfunction of this system, we have to diagonalize this, and we can do in straightforward manner to get these eigenvalues in this invariant subspace is this lambda plus minus lambda 1 and 2, and corresponding eigenvectors are this. And it is very straightforward to check that every invariant subspace we have PT phase transition subjected to that. If we put the condition to have these eigenvalues real. So if we can always put a condition to have these eigenvalues real, and that will leads to the PT phase transition in every subspace of this. Okay, so it is of these states are also eigenstate of this. Okay, now next one-dimensional example we'll consider not only exactly solvable system, but you can see the PT phase transition in the quasi-exactly solvable. Quasi-exactly means for the some particular integer value of some parameter in the potential, you can find those many states exactly. And in principle, you can go higher and higher values of that parameters. Okay, so this is a very nice example. Without, of course, this I is the double sign hyperbolic Gordon potential, and it was a quasi-exactly solvable system. And we make this is a potential in a PT symmetric non-Hermite system by putting this I. Here parity transformation we have used in a general x going to a minus x, which is a reflection about x equal to a by 2 axis. And rest is same. So now in this problem, what very interestingly we found that if m is even integer, we will never have a PT phase transition. The eigenvalues always comes in complex conjugate pair, and there is no way to make those eigenvalues real. But when m is odd, you can understand from common understanding that odd number of values cannot be divided into complex conjugate pairs. So in this, when m is odd, we can always put a critical value on this parameter such that the spectrum is real, and not only that, corresponding eigenstate also respect the PT symmetry. So you can have we have checked analytically for some lower values of m odd, and also quite a high value for m numerically. So you can have PT phase transition even in this quasi-exactly solvable system. And you can understand that this system is related to this system, this cos 2x, this is cos hyperbolic 2x, by anti x going to ix transformation kind of thing. So this is also shows exactly same behavior. Okay, now let us go to some higher dimensional systems. So we consider a first two-dimensional anharmonic oscillator with a very simple non-Hermitian PT symmetric interaction term. And we start with this, it's anisotropic, so omega x not equal to omega y. And we'll see that this is a PT symmetric potential. Okay, but in two-dimensional, as you know, the parity being a improper Lorentz transformation, it has different properties, that x going to minus x and then y is same, or x going to x and y going to minus x. So this one of the coordinates will go to minus, and time reversal will take I to minus I, lambda is real. So this is PT symmetric system. Very interesting feature we obtain in this particular system, that for a critical value of lambda, we can have a PT phase transition, but this lambda critical depends on omega minus square, which is nothing but omega x square minus omega y square. That means that depends on the anharmonicity, anisotropy of the, sorry, not anisotropy, anisotropy of the system. So if the system is isotropic, then this lambda critical is 0, and we cannot have a unbroken phase. Okay, so it will be, because this you can always have in the so if the system is more anisotropic, then the span of PT unbroken phase is wider. So if it is isotropic, then this there is no unbroken phase. System will be always in the broken phase. So the rotational symmetry, which leads to isotropy of the original Hamiltonian H0, seems to complementary to the unbroken PT symmetry of the PT symmetric non-Hermitian system. So this we realize for this particular system, and then we consider another simple harmonic oscillator, but this time we start with a isotropic oscillator in 3 dimensions, but in the external magnetic field. So again, we realize the similar physics because this external magnetic field introduced anisotropy in the system. And if you simplify this by considering magnetic field in z direction and taking the vector potential in symmetric gauge, we can have the anisotropy introduced in this system. And we can have energy eigenvalues and eigenfunction explicitly we calculate, and we found there is a phase transition in this depending on the strength of the magnetic field or the coupling the angular frequency of this system. So what we obtain is that if the magnetic field is sufficiently weak, less than that, and then we can always have or the oscillator frequency omega is greater than the half of the cyclotron frequency, then we can always have the unbroken phase with entire real spectrum and the wave function respect the PT symmetry. On the other hand, if you have your strong enough magnetic field, and then the symmetry will be broken. Or if you have the frequency is less than the half of the cyclotron frequency, then omega 1 will be complex and the energy spectrum will be complex. Okay, so with this, let me go to some models in the relativistic quantum mechanics, which we studied and obtained very interesting features. So we consider a Dirac oscillator in presence of magnetic field and with the imaginary spin orbit coupling Rasbach type interaction, which is sigma cross pi z this. And we consider magnetic field to be in the z direction, and this is the Dirac oscillator potential. So this model can be exactly solved, and this is a massless particle in that sense. So you can have features of graphene, a surprising material, which was a lot of excitement in previous 1.5 decade, and you can solve this system, but here since in relativistic quantum mechanics in 2+1 dimension, you will have very typical transformation properties of parity transformation, which I have wrote. So this already we know for 2-dimensional case, but then in the relativistic analog of this transformation, this parity transformation will be associated. If I consider P1 parity transformation, then parity operator will be associated with the sigma Y matrix, and if we consider P2, then it will be associated with the sigma X matrix. And of course, time reversal is I going to minus I, Px going to minus Px, and Py going to minus Py, and it will be the I sigma Y in the usual time reversal in the Dirac theory with the complex conjugation. Okay, so this is the now this model is PT symmetric non-Hermitian, either P1 T symmetric or P2 T symmetric, and we can exactly solve this model, and you can find energy eigenvalues and the mass gap for this system, which is given by this, and we can put the condition on this magnetic field or in the this parameter k1 such that we can have a real spectrum, and that we have and that will give you to the PT phase transition. So if lambda square is less than this, that lambda critical square, or the magnetic field is greater than this, which is greater than the critical magnetic field, then we can have real eigenvalues, and one can check that the eigenstate respect the symmetry, and we have PT phase transition. So this I have plotted, and this energy eigenvalues they versus this lambda. So this is the lambda critical. After that, this is the broken phase. This side we have unbroken phase for different quantum numbers. And similarly, with respect to the magnetic field, so this is the magnetic field. So if you have the strength of the magnetic field is greater than this, then you have unbroken phase in this side and broken phase if you have the weak enough magnetic field. Okay, Most interesting thing is that we all know that experimentally it is observed that graphene has some non-zero mass gap, and only in the unbroken phase you can get the mass gap non-zero and real mass gap, and which is consistent with the experimentally observed values. So it's proportional to square root of the strength of the magnetic field. So that the properties of this mass gap is obtained only when you have in the unbroken phase. Okay, so this is all about the initial introduction of PT phase transition in the various one-dimensional non-relativistic as well as relativistic quantum mechanics. With that, we'll now go to the some models in quantum field theory. So we'll consider one model which was discussed in details yesterday by Peter Millington in his talk, that we consider a non-Hermitian theory of charge scalar, that we have two scalar field phi1, phi2, and we did this mass term which is non-Hermitian. So this mass term is non-Hermitian. All these m1, m2, and mu are real. So this is a non-Hermitian model, and we will see the phase transition here. Before that, if we denote these fields as a doublet, and then it is easier to write a PT properties of these fields. So phi will be this some matrix types phi in this doublet, and similarly time reversal will give the some matrix times phi star. And P and T are now 2 cross 2 matrix because it is a 2 cross 1 vector. So as is shown by Peter's talk yesterday, that this P operator, this parity operator should be 1 and -1. That means the phi1 transform as a scalar, whether phi2 transform as a pseudo scalar to have a parity symmetry in that. And the choice of the time reversal under which the Lagrangian is PT invariant is T should be the unit in 2 cross 2 dimension. Okay, so this is the transformation properties of these fields. Now, as long as the symmetry is constant, P and T can be interchanged. Of course, this can be interchanged, but we prefer to have this. Okay, now the if you find the eigenvalues, this is a mass matrix, and mass matrix is a non-Hermitian mass matrix. So you can have these eigenvalues, and we can find the corresponding eigenvectors of this mass matrix. And you can see that if for m1 square minus m2 square mod is greater or equal to 2 mu square, then it is unbroken PT symmetry. You will have a real eigenvalues, mass eigenvalues to mass matrix. And if you have it is less than mu square, that means this will be complex imaginary part, and then it will be broken. And the eigenvectors also they will. But this this particular methodology will be using for SU and gauge theory. So when we discuss our main interest in the PT phase transition in SU and gauge theory QCD, then we'll use this techniques. So similar things will be encountered in non-abelian model. Okay, and before I go to the non-abelian model SU and theory, let me comment about the C symmetry. See, the eigenvalues of this non-Hermitian mass matrix does not change if you go to mu squared to minus mu square. So if you look at that, if you go to mu square to mu to the power 4, so mu square going to minus mu square, it will not change. Okay, so so this symmetry implies that there is a associate symmetry which is can be related with the charge conjugation or C symmetry in our non-Hermitian literature. So charge conjugation symmetry you can define phi going to some matrix and phi star, and we can see that it's C is actually the P matrix, the matrix for the parity transformation. So the CPT invariant in both PT broken and unbroken phases, and in broken PT phases, this violates CP but preserves CT symmetry. Such charge conjugation symmetry exists in the non-abelian model also. Okay, so with this basic introduction, so let me go to the non-Hermitian model, that is the PT symmetric non-Hermitian SUN gas theory model. Okay, so at low energy QCD can be effectively expressed in terms of abelian degrees of freedom. The off diagonal gluons attain large mass, and below that mass scale, the diagonal gluons become off diagonal gluons become inactive and hence decouple. And dominant degrees of freedom of that theory is the diagonal gluons. So if you start with the SUN gas theory, and if you have reduced by when this off diagonal elements acquires mass, then you reduce with n-1 copies of abelian gas. This is called the abelian projection, and well known in this literature of QCD. And this abelian dominance is generally studied in some particular partial gauge fixing known as maximal abelian gauge. We have worked in maximal abelian gauge with the BRST symmetry, etc. But here, what I'm going to discuss is there is a new gauge symmetry introduced a couple 3 years ago by Raoul and his collaborators, that quadratic in the fields for each A group. And this gauge is used to show that mass generation of off diagonal gluons are very useful, and this gauge is very useful to show the abelian dominance. And this effective Lagrangian in this will have this. And ghost, there is no ghost propagator because there is no ghost kinetic term. So the ghost interacts only through this interaction term. Now, if there is no propagator for ghost, so when the ghost condensate, this term will have only the quadratic in gauge fields. Okay, so and there will be the mass generation, gluon acquires mass, and that mass matrix is given by 2G. I'll show you this a little bit explicitly in terms of this ghost condensation. So diagonal gluons are massless due to antisymmetric properties of this. So this is antisymmetric so this only the diagonal elements will be 0 massless, and off diagonal element will be antisymmetric, have the antisymmetric property. Okay, so now there are two different gauges in this, one in the normal deconfined phase, normal phase or deconfined phase, and another is the ghost condensed phase. So in the normal phase, this is the Lagrangian, and we note that the ghost Lagrangian does not have the kinetic terms, as I mentioned already. They act like auxiliary fields, and in the normal phase, but they play an important role in the infrared region. That I already said, that ghost Lagrangian contains a term. So if you break this term, there will be del mu C, and there will be F ABC. CA and A term. So this A and A term, there will be two the gluon fields, and then there will be two C bar A and C bar C terms. Okay, so now hence when ghost freeze, they amount to a non-zero mass matrix for the gluon. So when this freeze, then this will be a C number, and this will be in quadratic in gauge field, so it will be treated as a mass matrix. Okay, so hence when ghost freezes, they account to a non-zero mass matrix for the gluon as follows, that I already mentioned. Okay, but in SUN symmetric state, this ghost anti-ghost condensates are identical. So this can be shown, and let us denote with this number K, and this mass matrix now becomes 2G K times this K comes out of the sum, and C1 to N square for all these generators, so SUN, so FABC. So this is of course antisymmetric matrix, and of course a non-Hermitian. M square dagger is not equal to M square due to the antisymmetric structure constant. Okay, so now now this mass matrix is unique to unique, it has n minus n non-zero eigenvalues, and only, and because diagonal elements, n minus 1 diagonal elements are massless, so there those are 0, and off diagonal gluons often the mass. So this due to the antisymmetry, eigenvalues are purely imaginary. This eigenvalues are due to antisymmetry. These eigenvalues are imaginary, and they occurs in a conjugate pairs. So the massive off diagonal gluons are inferred as the evidence for the abelian dominance, because they below that scale they will be inactive, and only diagonal part will survive. So that is the evidence for abelian dominance. Another evidence is that since mass square of the off diagonal gluons is purely imaginary, hence the pole of the off diagonal gluon propagator is in the imaginary p square axis, which is another important signature of color confinement. So this mass for gluon generated through a given dynamical mechanism breaks the gauge symmetry as usual, but there are mechanisms to provide mass to the gluons in a gauge invariant way, so I'm not going to discuss. Thus we see that the ghost condenses acts as the QCD factor. Okay, so in the ghost condensed phase we have the Lagrangian. Now we have this mass, dynamically generated mass, and this so in the condensed phase we have, this is the effective Lagrangian. So for example, if you consider n equal to 3, that is SU3 gauge 3, so M3 square and M8 square, these diagonals there will be 0, they are still massless, and off diagonal gluons will have mass square that and this will be same as the 1 2 position and 2 1 position, so it will be I m1 square, so m2 square will be minus I m1 square. Similarly, m4 and m5, m6 and n7, so only 3 m1 square, m2 square, m3 square, they are real positive numbers. Okay, the gluons 1 and 2 can be considered as the conjugate to each other. This and this are conjugate to each other, and if you have this mass matrix, you can write explicitly for SU3 is this half m1 square, this term will be positive, and this term will be negative. Similarly, for all will be one term will be positive and one term will be negative. Okay. Now we come to the hermiticity properties of this Lagrangian in two different phases. Okay, so this effective Lagrangian in the normal phase, this I wrote many times. So this again I wrote this effective Lagrangian, and hermiticity properties of the gluons is well defined, and they describe with real degrees of freedom. So it must be with a Hermitian. These gluons are Hermitian because they are real degrees of freedom. The hermiticity of ghost fields remain unclear, as the operator of conjugation in principle transfer particle to antiparticle, and the following for a detailed discussion I refer to this famous paper by Kugo and Ojima and long ago 1979. That very nice discussion that what should be the hermiticity properties of ghost fields. And since they transform to the particle to antiparticle, so it is natural to natural choice of the hermiticity properties of ghost field at that Ca dagger should be Ca bar. So particle will go to, and the Hermitian conjugate will go to the antiparticle, or vice versa. But in usual literature, this hermiticity properties of the ghost field was taken in a different way to maintain the to put the theory in a Hermitian way. Okay, so under these hermiticity properties of the fields, we can see that this term is of course Hermitian, because if you take a dagger, you will get this. But the term in the ghost interaction term Ca del mu Ca, this is not equal to its Hermitian conjugate. Okay, so I'm sorry. Okay, so the Lagrangian in the normal phase is not Hermitian because of this natural choice of this hermiticity of the ghost fields. So effective Lagrangian in the ghost condensed state phase, or this confined phase, is also not Hermitian, as the mass term for the gluons is purely imaginary. The mass term is now mass term is now non-Hermitian. Okay, so but that non-hermiticity is profound in that sense, since gluon condensate, this non-hermiticity of this mass term is independent of the choice of the convention of the hermiticity properties of the ghost, because it always occurs in ghost, anti-ghost, and they are taken in the condensed state. So this non-hermiticity in the confined phase is due to the non-Hermitian mass matrix. Okay, so that is why we said it's profound. And also the Lagrangian, we will also mention about some inner automorphism symmetry in the theory. So if I have defined this Lagrangian piecewise like this term, then if we take some inner automorphism that changes the group indices, then under this L1 will be go to L2, and L4 will go to L5, L6 similarly. And this will, if we put additional to the theory, then in the broken phase and this confined phase, it is have a extended hermiticity. Okay, so you can restore the hermiticity by this additional properties. Later we'll understand that this property has a relation to the C symmetry of the theory. Okay, so this inner automorphism in exchanging the group indices that what I wrote in that expression is basically can represent by this matrix. It is basically the interchange of group indices from 1 to 2, 4 to 5, and 6 to 7, 6, 7 interchange, and 3, 8 interchange. Thus, we have shown the both in normal and in the confined phase, the system is non-Hermitian. Later being profoundly, because it does not depend on the hermiticity properties, convention of the hermiticity properties of the ghost. Now we go to the transformation, so parity and the discrete transformation, parity and time reversal transformation of these fields. So gluons, this is they transform as a vector, so it is like this, and all gluons transform in the same way. So parity is a linear operator, and the ghost field normal phase in invariant under the parity. If we choose the ghost under parity, they transform like this. Of course, we could have chosen with the plus sign, but ghost being scalar under parity is there because they are scalar under parity and equally accepted in the plus sign. However, we feel that the parity transformation is about more suitable for ghost as they are anti-commuting scalar. Okay, now so in case of time reversal, it is not that straightforward, because in SUN generators, some of the generators are purely imaginary and some of them are real. So the time reversal transformation, which is an antilinear transformation, it is little bit tricky. Some of the generators has a different transformation from the others. Okay, so for SU3, for example, if we consider that group index is 2, 5, and 7, they are imaginary, so they have this kind of time reversal transformation. On the other hand, the 3 and 8 are diagonal, and 1, 4, 6, all these are real, so they will have a different. So the real for real generators and the imaginary generator, they will have a different transformation properties under time reversal. Okay, so overall the field strength tensor will have a under time reversal will have a plus minus sign, so it will be invariant in the normal phase. So in the action in the normal phase, invariant, so I mentioned, and the time reversal properties of the ghost field now we define. So they will have again for the group indices for 2, 5, 7, and the rest for SU3 will be different. So that the time reversal properties of the ghost are defined for P and Q. Q is for the imaginary, the 2, 5, 7 for SU3, and this rest is P. So P denotes those group indices, Q denote the imaginary. Okay, so then we have this antilinear makes two sets of ghost transformation in the completely different manner, and thus the theory is in the normal or the deconfined phase is individually both parity and time reversal invariant. So in the normal phase, they are in both invariant. But to check that parity is still symmetry in the even in the Ghosh condensed phase, but time reversal symmetry is broken due to the pure complex nature of the mass term. So the symmetry is broken due to the complex nature of the mass term. So this mass term, which you can be explicitly written, and under time reversal, it's change sign, even though it's. So also PT psi is this eigen vectors of this mass matrix. They are also not equal. So this condensed phase is now we can understood as a broken PT phase. So PT symmetry is violated in this condensed phase, and we can see that the antisymmetric nature of the structure constant appearing in the mass matrix has led to this breaking. Okay. So now, so this we realize as a PT phase transition from normal phase to the deconfined phase of Hessian symmetric gauge condensate is identified as PT phase transition. And associate between the color confinement and the spontaneously breaking symmetry in this model mechanism independent, even though this model is link is through the ghost condensation. So ghost condensation actually takes the role of the order parameter, which leads to the. So when we have a PT phase transition in some non-relativistic in some quantum mechanical system, we find there is some parameter which is responsible. By changing that parameter, we can go from the broken to unbroken phase. So similar role is played by this ghost condensation. Okay, so there is a difference between this order parameter I was talking about. So in case of the complex scalar model, we had this eta which plays the order parameter role of order parameter. In case of SUN gauge theory, the ghost condense the bilinear this CSC bar. This will play the role of this parameter. Now, towards the end, let me mention about the C symmetry about this. So we show that the set of quantum field theory is we already introduced the inner automorphism provides the internal symmetry, and that is analogous to the C symmetry. So as we know, the C symmetry is independent of PT symmetry, so its commute is 0, C square should be 1, and it commutes to the Hamiltonian. So we'll see that inner automorphism, which we introduced earlier, satisfy all three properties, and we can identify that as the C symmetry. First, that inner automorphism exchange the group indices that we mentioned. So Lagrangian in the initial unbroken theory in the normal phase, sum over all group indices. So it is sum over all group indices. So if you interchange the group indices, this will be remain invariant. Since the Lagrangian in the normal phase remains invariant under this inner automorphism. Thus, QFT analogous of this condition satisfied. And PT is a space-time symmetry, and their inner automorphism is only the group space. So it is a completely independent. So PT and C, that inner automorphism is commute or independent of PT symmetry. And third condition is trivial, because if you interchange 1 to 2 and then 2 to 1, then it will be the same. So C square is supposed to be the. So it is clear in the theory both that phases has the CPT invariant, and then the broken PT phase theory violates the symmetry and preserves the CT in complete analogy with the scalar model. Okay, so I come to the, I hope I am within time. I come to the conclusion. This first and a novel example of non-Hermitian gauge theory exhibiting phase transition is presented in this, and we consider the natural hermiticity properties of the ghost field, and found that the SUN gauge theory in normal as well as the condensed phase both are non-Hermitian and systems, and we have the symmetry is broken in the condensed phase. So transition between QCD phases is identified as the PT phase transition. It's just identified. So Ghost condensation plays the role of order parameter in this. And as I mentioned just now, C symmetry is the inner automorphism. So we can have a consistent non-Hermitian gauge theory. Okay, thank you.
Thank you, Babani, for the nice talk. And now we are open for questions. So there is one question in chat box by V. Chitika Ruby. Do you want to ask the question or?
No, sir, actually, it's no, sir. It's a very basic doubt, sir. It can be cleared.
Okay. Okay. Thank you.
Okay. So any other questions? Okay. So if there are no other questions, let's thank Babani again for the nice talk, and I'll use this opportunity to thank Babani for it has been a very nice experience to organize this program together with him. So thank you, Babani.